Hey, everybody. So we're going to do an example here of using the derivatives to help us come up with a graph for a function. So here's the function I want to do. And our general strategy, we're going to use the derivatives and the function itself, the derivatives being the first and second derivatives, and the function itself to collect information about the function's graph, the behavior of the function, and see if we can put that information together into some kind of coherent graph. And again, the point isn't that we need to do this because we don't have graphing software. Of course we do, but we're trying to build some intuition about how functions work, how different types of expressions, when we combine them, what are those combinations cause? How do they end up playing out when you have different values of x? So let's jump in. I like to compute my derivatives first. And then once I have all the derivatives, because sometimes the derivatives can be a little ugly, you get a whole bunch of algebra and it can kind of, to my mind, disrupt the flow of thinking about the picture of the graph. So I just want to get that part done and then go through each one and collect the information I need. So our derivative, we'll have a couple of power rules here. So we get -3 x to the -4th, and then a -2 comes down. We already had a negative, and we've got -3, and we can factor out. We've got, looks like an x to the -3 will work, and then I've got what, -3x to the -1 plus 2. Okay, so I've got two versions of the first derivative here. And I'm noticing I like them both for different things. For the next step to take the derivative, I'm going to use that first version where it's just a sum of a couple of terms, because that's pretty easy to take the derivative of. The second version is going to be useful to me when we want to find critical values, places where this function doesn't exist or where it's equal to 0. That's an easier form in my mind to do that. I like the factors in dealing with them. So I'm actually going to be using both of them. But when I take the derivative, I'm going to look at that first, the -3x to the -4th plus 2x to the -3rd, right? If I use the other one, it's fine, but I would have to use a product rule, and I think it'll just be a little bit messier. But looking straight above here, the -4 comes down. I get 12x to the -5th minus 6x to the -4th. And again, I can factor out an x to the -4th, and it looks like I can also grab a 3 when I do that. So I'll have 4x to the -1 minus 2. And that looks like that's going to be our 3 derivatives. Just put them a little, keep myself with lots of space. And again, I'm going to keep both versions of that second derivative because I think depending on what I'm doing, one or the other might be useful. So now I'm just going to go through and collect information. My function tells me a few things. So from f of x itself, I'm going to get, first of all, my intercepts. Right. So let's throw up a factored version of this as well. That seems useful. And I just like the symmetry of them all having it, right? So remember, my intercepts are the value at 0. What is f of 0? And in this case, f of 0 does not exist, right? The function isn't defined there, so there's no intercept there. And then what about the f of 0 would give us the y-intercept, right? What's the value where it hits the y-axis? In this case, it doesn't. And then when we want to find the x-intercept, we try to solve f of x equal to 0. In this case, that's x to the -2 times x to the -1 minus 1 equal to 0. So here's where I like this factored form. This is 0 if either of these factors is 0. Well, the first one can't be 0. Right, 1 over anything. There's no number you can divide 1 by to get 0, so that factors out. And so all we need to find out is, when is this equal to 0? And of course, that's equivalent to x to the -1 being equal to 1. which happens at x equals 1. All right, so we have an intercept there at the point. Actually, let's circle the point, not just the x value. At 1, 0, we cross the x-axis, and it looks like that's the only place we're going to do that, right? So that's some good information for us to have. Let's look at a couple other things. I want to know the sign of my function. When is it positive? When is it negative? Right. So the idea here is we've got this function that doesn't exist at 0. It's probably going to have an asymptote there, and hits the x-axis at the point 1, 0. All right. So let me sketch out a number line. Whatever it does, it can only switch from positive values to negative values at these 2 points, right? Because everywhere else it's continuous, right? This function is continuous except at x equals 0. We can perform the operations given on any other number. It's continuous. We know that these are both rational functions. We're adding them together. Those are continuous everywhere in their domain. And the sum or difference of continuous functions is continuous on their domains. So this function is continuous everywhere but 0. And so the only places it can jump from positive to negative are as we cross 0, because we might have an asymptote and it can do different things on either side of it, or at the point x equals 1 where it goes right through. If it were to cross anywhere else, we would know about it. We'd have a 0 there. So if I want to know the sign of the function, I can simply think about the sign of any point in these 3 regions and know that the sign stays the same through those regions. So for instance, let's think about x below 0, right? So I can just take any number I want and put it in for, like, I can evaluate f of -1, right? We're going to have, notice what's going to happen. X to the -2 is always positive, right? 1 over x squared is positive, but we're subtracting it, so this thing is always negative. And then x to the -3 is going to be negative when we put in a negative number. So in this case, we're going to have -1 minus 1 or -2. So I know that things are always going to be negative down here. Okay. Between 0 and 1, I'm going to look at these 2 factors. So let's write that down here. Remember that f of x is x to the -2, x to the -1 minus 1. And just think about these factors. Again, this first factor, x to the -2, is just positive, 1 over x squared. So now I'm putting in a number like, well, let's just do something like 1/2. This is going to be 2 squared times 2 minus 1. This is going to be 4, or positive, right? So I'm putting in numbers less than between 0 and 1, but I'm taking their reciprocals, so they're bigger than 1. So this factor is positive. And then the x to the -2 is always positive, so it's positive there. And then finally, for numbers bigger than 1, something interesting happens. X to the -3 is always going to be smaller than x to the -2, because if you take a big number, like not even that big, but anything bigger than 1, and you cube it, that's bigger than squaring it. So the denominator of x to the -3 is bigger than the denominator of x to the -2, which means it's a smaller fraction. So that's always going to be negative. So let's just make that clear. If I do something like f of 10, this is 1 over 10 cubed minus 1 over 10 squared, right? So maybe it's easier to see this way. This one's always going to have a bigger denominator. So that's a smaller fraction, right? This is 1/1000th. I could change this to 10/1000ths, and we know that that's less than 0. So my function is negative there. So now I know in my graph, there's only one little region where the function's positive, between 0 and 1. Everywhere else, it's going to be negative. Okay, so we're starting to get a little picture. We know it goes through this point. What else can we say? Let's think about what happens at 0. At 0, both of these terms, 1 over x cubed and 1 over x squared, go to infinity, right? Meaning if we get closer and closer to 0, they can be made as large or as small as we want them to be, depending on the sign, right? So it might be going to positive, I shouldn't say as small, as really as large, negative. So let's think through the asymptotes. Let's think about the limit as x approaches 0 from above. I'm going to write the function this way. So if we're putting in really, really, really small numbers and taking 1 over, well, here, we'll do it this way. The limit as x goes to 0 from above, x to the negative 2, just using a limit law. We know that this goes to infinity, right? That was one of our rules about these kinds of limits, about asymptotes. If you have 1 over x to any power, you're going to go to positive or negative infinity, any whole number power greater than 0. And so in this case, it's only positive. So this term is giving us increasingly large positive numbers. And so is this one, because as we get close to 0 from the right, we're putting in positive numbers that are really small. We're getting really big numbers. We're subtracting 1, but who cares? When you're putting in something like 1 billionth, you get a billion out, you subtract 1. But in both cases, we're getting large positive numbers. This limit goes off to infinity. As we approach from below, we get almost the same thing happening. This first term, we're now putting in negative numbers, but remember this one has the squared part. So that first term is going to be, again, shooting off to positive infinity, but the second factor, because we're putting in negative numbers, we're approaching 0 from below, this x to the negative 1 is really large negative numbers. We subtract 1, which only makes them more negative. So we've got a really large positive numbers times really large negative numbers. We're getting really large negative numbers. So this is going towards negative infinity from below. So we have an asymptote at 0, and now we have a little picture of what that asymptote looks like. From above, it's shooting off towards positive infinity, and from below, it's going down towards a negative infinity. What about our end behavior, meaning what happens as we go further and further away from 0? So we're going to just use some intuition on here. We haven't quite developed the rules to do this with more rigor, but I think this particular function is easy enough to think about. The limit, well, let's just say it plainly or semi-plainly. So as x gets really, really big, right, what's going to happen to f of x, right? Well, it has these two. Let's write this in, oops, not 3x cubed over x squared. These two things, as x gets really, really big, are two incredibly small fractions. And so we're subtracting a billionth from a trillionth and getting a really tiny, tiny number, right? And so and we can make them as small as we want. If we just keep taking x larger and larger and larger, these fractions and their difference are just going to get incredibly small. So we say that they go to 0. Right? And the similar thing is going to happen in the other direction. It doesn't matter that we're putting in negative numbers. They're getting incredibly large. And so in both directions, this function disappears, right? We can make it as small as we want by taking large or really large negative numbers and putting them in for x. So that's a whole bunch of information we've got from our function, okay? So we're going to leave this alone for now. We'll come back to all of that. Let's look at our derivative. F prime of x was equal to, I'm going to look at the factored form we came up with up above, -3 x to the -1 plus 2. So the first thing I want to do is find the critical values. This is where the derivative doesn't exist or where it's equal to 0. So our critical numbers, we still have a problem at x equals 0. We can't have 1 over 0. And then we need to solve when does this derivative equal 0? In other words, when is this equal to 0? Well, we know the first factor can never be 0, just as we saw before. So this is only 0 when we have this equation satisfied. This is equivalent to 3x to the negative 1 is equal to 2. And then we get x to the negative 1 equals 2/3, which means x is equal to 3/2. Okay, so we have critical values at 0 and 3/2. We know 0 is a critical value because the derivative doesn't exist, and we've got a decent handle on what happens there. We'll still use it in a moment. X to the 3/2 being a critical value means it's a candidate for a maximum or a minimum, right? Because the function exists there and we've got a 0 derivative. So let's evaluate that point. This just gives us a nice anchor point when we're doing our graph. So f, right, I'm evaluating the function, not the derivative there. I want to know the value of the function just to get another point in. And so this is going to be, what do we have? We'll have our function, oh yeah, to the negative 3/2 to the negative 3 minus 3/2, oops, that's not a 3, 3/2 to the negative 2. This is going to be 2/3 cubed minus 2/3 squared. So we're going to get 8/27 minus 4/9 or 8/27 minus 12/27. So negative 4/27. So what is that? 1/7, which is about, so we'll just do an approximation, negative 0.14. Just so when I'm graphing this, I'll have about where, you know, it's pretty close to 0. So we're going to have the point 3/2, negative 0.14. As a possible max or min. We'll see shortly which one of those it is, if either. So our next step is to see what is the sign of the derivative at various regions using those critical values, the critical values of 0 and 3/2. Okay, so we want to, again, take a look at, we want to know what the sign of this thing is, right? So let's start with our negative numbers. Let's put in something like f of 1, right? The same argument we made a minute ago. This function, this derivative, which is itself a function, is continuous everywhere except at 0. And so the only way for it to switch from negative to positive is to either, as we cross that 0, because it's discontinuous there, and so it can jump from negative to positive, or it has to pass through the x-axis, and we know the only place it does that is at x equals 3/2. So to find out if this thing is negative or positive below 0, one method for that is just to evaluate it at a convenient negative number. Negative 1's a really convenient negative number. It's easy enough to evaluate. X to the negative 3, if we put in negative 1, is just negative 1 to the negative 3, which is still negative 1. And then we get negative 3 times 1 over negative 1 makes this a positive 3 plus 2. And this is negative, right? We've got a 3 plus 2 times negative 1 is negative. We don't really need to know what it is. Obviously, you can compute that, but the point is that it's negative. And because it's negative there at negative 1, we know the function can't cross that x-axis anywhere before 0. And so everywhere else, it's negative below 0, okay? Let's do the same thing between 0 and 3/2. And a very convenient number there is 1. That's easy enough to evaluate. We get 1 times negative 3 plus 2, which now is negative, right? And so we're going to have negative here as well. And then let's look at above above 3/2. So let's look at something like 2, right? That's above 3/2. F of 2 is going to be 1/8 times -3 x to the -1. So that'll be times 1/2 plus 2. And so that quantity is positive. The 1/8 is positive. This is greater than 0. And so we get positive there. So the function is decreasing below 3/2, except where it doesn't exist. And it's increasing above 3/2. Okay. This also means that there is a local min at x equals 3/2, because we see that the function's decreasing as we approach 3/2 from below, and then the function starts to increase afterwards. So we've got this little dip. Okay. We can't argue that it's a absolute maximum. We know the function keeps increasing forever above 3/2, and if we're going backwards, right, this side that's decreasing towards our local min, all the values over there are going to be larger. So it seems like maybe it's going to be an absolute local min, but then we've got this discontinuity at 0. We don't know what the function does there. It could jump to some completely different value well below this one. So we can't really argue anything about absolute max or min right now. We might be able to figure this out as we move forward and put all of our information together. All right, so let's just write this out explicitly. F of x is decreasing on -infinity to 0, unions with 0 to 3/2. And then f of x is increasing on 3/2 to infinity. Okay. All right, so there is our first derivative and all the stuff that we wanted to get, all the information we get from that. Let's finish up with our second derivative. I'm going to write that factored form again. We had 3x to the -4th, 4x to the -1 minus 2. And same process. We really just want to know where this thing is positive and negative. And so we don't, I don't usually see them called critical values, but the places where we can switch sign. So I'll just call them our, let's say the, well, whatever, we'll call them our pseudo critical numbers, right? So the critical numbers here, we know the function, the derivative doesn't exist. The second derivative doesn't exist at x equals 0. And then we also need to find out where it is equal to 0 itself, which just like the last two times, this first factor can't be equal to 0. So this means we're looking for the place where this is equal to 0. We add 2 to the other side. Divide by 2, we get x to the -2. Oh, that's not squared, that's positive. Sorry, that's just to the -1 power. That's why my memory was saying there was no square root in this. So divide both sides by 4, we get 1/2. So that means the reciprocal of x is 1/2. So x must equal 2. So now we're looking at a number line where our points of interest, all that same reasoning. We just need to check a point on each, in between each, and one point in each of these three intervals, below 0, between 0 and 2, and above 0. So I'll just start again, evaluating a convenient number. So 3x to the -4, when we put in -1, we get -1 to the 4th power, which is +1. We're taking the reciprocal of 1, but that doesn't do anything. So we just have a 3 there. And we're putting -1 into x to the -1. -1 to the -1 is -1. So that becomes a -4 minus 2. So this is less than 0. Negative times a positive. We got a negative here. Let's evaluate between 0 and 2. 1 is a nice convenient number. We got 3, 4 minus 2. This is greater than 0. We're positive in here. And then let's do f double prime of something. big enough, looks like 10 will work. So we're going to have 3 over 10,000 over 4/10 minus 2. The relevant part is that this is negative, the other one's positive, so this thing is less than 0, and we get negative there, right? We don't need to know the values of these, we just need to know if they're positive or negative. That's all we're interested in there. So this tells me that my function, f of x, is concave up on 0 to 2, which confirms that local minimum at 3/2, remember, that's in that interval and that concave up shape like that. And then f of x is concave down. It's going to be negative infinity to 0, union with 2 to infinity. Okay. So now we've got a whole bunch of information about our function. Let's try to graph it. I'm going to try to remember, I've got most of it written down here, the information we have. So what did we just come up with? We have an asymptote at x equals 0. And I think what I'm going to do for myself is just, I'm going to do the graph over here. But the asymptote, what we figured out was that as we approach it from above, we go to positive infinity, and as we approach it from below, we go to negative infinity. So I'm just going to draw that there as a reminder to myself. We also found from our function that f is greater than 0 when x is between 0 and 1, and it's negative everywhere else. So let's also, and we also saw that it went through the point 1, 0. So I'm going to go ahead and put the point, let's do our graph in red. There's the point 1, 0. We'll put my asymptote as a dotted line on top of the axis. So this function is positive between 0 and 1. So I know it's going over here, and then it's negative below 1. So I'm just drawing that little bit. And I don't know yet, but all I know, below 0, the function is negative. I'm not going to draw anything because there's no, like, I don't have an anchor point over there. I also know that the function goes to 0 as x goes out to infinity. That was one of the things we said, that as x goes to as x gets larger and larger, the function gets smaller and smaller, and it doesn't matter if we're going to positive or negative infinity. So what that tells me is, I know my function's negative, for instance, above 3/2 or above 1. Here's x equals 1. So out here, it must go back towards 0. And I know my function's negative on the left half of this graph, and I know as we get larger and larger negative values out to the left on my graph, the function must be approaching 0. So I might end up erasing those as I get more pieces in here, but that's just a little visual reminder for me that what the function does out there. Let's see, what else do we have? From our first derivative, we know that, we had an absolute minimum, not an absolute minimum, a local minimum at 3/2, and then a very small number. I'm going to exaggerate it. It was negative 0.14. So this is the point 1. No, not the point 1. It's 3/2. This is the point 3/2, and something about negative 0.14. I think it was. Yeah, that's about right. Okay, so I'm just going to draw it there. We know that our function is, so the information we got earlier is that our function, for instance, below, let's just write it, f of x is decreasing if x is below 0. We also know that f of x is concave down if x is below 0. That was the piece of information we just have. So I have enough information now to draw this left half of the function. I know I have an asymptote. Remember our asymptote up here. And all of this information fits in nicely together. Here's a function. Let me redraw this a little more nicely. Here's a function that's approaching 0 as we go towards negative infinity. It's decreasing and concave down with an asymptote going towards negative infinity at x equals 0. So that's how all that information fits together. So we've got that piece of our graph. Let's look between 0 and 1. Remember, this is the point 1, 0. Between 0 and 1, my function will be decreasing. F of x is decreasing. Between 0 and 1. Right, that was part of our, between 0 and 3/2. I'm looking at 0 and 1 right now, but it's this is where it's decreasing. We got that from the first derivative. And we know it's concave up there from the second derivative. It is concave up between 0 and 2. And so I can now draw this little piece of the graph. We have this asymptote, we're concave up and decreasing. So I'm increasing because I'm drawing backwards. I also know that it continues decreasing all the way down to this point here. Then it increases, right? So after 3/2, it starts to increase and it's concave up. Let's write this out. F of x is increasing if x is greater than 3/2. So after that minimum, it continues increasing forever. But we also have that f of x is concave up. Well, we've got this here, concave up from 0 to 2. F of x is concave down when x is greater than 2. So what that means is, so let's mark off 2 at about right here. We're concave up, and then here we switch to concave down, and then we have this approaching 0 as we go off towards infinity. Okay, and there's our sketch of that function, right? I could redo these lines a little bit. Let's try that really quick. Let me just get rid of some of these. Whoops. And just put them in a little nicer. Now that I kind of have the, when I'm doing this on paper, what I typically do is kind of do a really rough sketch to begin with, and then try to make a decent one. It's nice to have it at least somewhat nice looking. There's my concave up, and then right at that point, I turn to concave down, and then I shoot off towards 0, or I approach 0 as x gets larger and larger. And there's a sketch of our graph, right? A function that was probably not obvious what it did when we look at it at first. This is our f of x is equal to x to the -3 minus x to the -2. But now we have a sense of its behavior, right? And so if this thing was something we were studying because it represented something we were interested in, we now know a lot about how it works, where it has this local minimum, right? So my drawing's a little off there, but we have a local minimum at 3/2, and we know about what it is, and we know that it increases after that. For instance, we know where these asymptotes are and what happens out at infinity. So that's it for this one. I'll try to get another example up soon. Thanks, everybody. I will see you next time.